let's now compare the reactivity of esters with that of amides in nucleophilic acyl substitution reactions. And again, as we have done before, we follow the same scientific path by looking at the electrophilicity of carbon of the carbonyl group in each of these two carboxylic acid derivatives, and then we can look at the leaving group ability. Now, in esters, this carbon of the carbonyl group is bonded to oxygen. Obviously, oxygen is more electronegative than carbon. Then this leaves a negative delta on oxygen and a positive delta or a positive partial charge on carbon of the carbonyl group. Carbon of the carbonyl group in amides is bonded to nitrogen. Obviously, nitrogen is more electronegative than carbon, which pulls electrons more toward itself in this CN bond. But a very important difference in these two inductive withdrawal is the higher electronegativity of oxygen relative to that of nitrogen. So oxygen is more electronegative than nitrogen. So therefore, this is a stronger inductive withdrawal. Of course, the higher the electronegativity of the atom is, okay, the higher or the stronger the inductive withdrawal will be. Not only that, we can also do resonance, by the way. This oxygen can actually donate electrons or delocalize electrons in this way. And if we do that, then we can get another resonance form. So that's possible. Here also, we can do the same. So nitrogen can donate its lone pair. And of course, if a double bond is formed here, as a result, this carbon-oxygen double bond is simultaneously broken to give this now resonance form. So we can do resonance in both, but nitrogen again is less electronegative than oxygen. So nitrogen here is less electronegative than oxygen. If it is less electronegative, then it has a lower or a weaker, if you like, a weaker ability to withdraw electrons toward itself in a covalent bond relative to oxygen. If it has a weaker ability to withdraw, then it will have a higher ability to donate. So nitrogen is less electronegative than oxygen. Therefore, it's a better electron donor. Nitrogen is a better electron donor than nitrogen. If it is a better electron donor than nitrogen, then this resonance is actually stronger. Therefore, this carbon is more electron dense as a result, because resonance donation is stronger, if you like. We can also write that. This is a stronger resonance donation. That's because nitrogen is less electronegative. That's also because nitrogen is a better electron donor. So that carbon of the carbonyl group, therefore, is more electron dense. If it is more electron dense, therefore, it is less electrophilic. It's less electrophilic than carbon of esters. Carbon of esters, obviously, is more electrophilic because of the stronger inductive withdrawal and the weaker resonance donation. You can also say that carbon is less, which is also correct, less electron dense. So the lower electron density of carbon in esters than carbon in amides, due to the stronger inductive withdrawal and weaker resonance donation, make that carbon actually more electrophilic. So therefore, in the nucleophilic addition step of a nucleophilic acyl substitution reactions, esters should be more reactive. That's because they contain the more electrophilic carbon, and therefore esters will be of a higher reactivity in nucleophilic addition reactions. We have seen just a while ago that esters are more electrophilic at carbon of the carbonyl group than that of amides, and that's because of the stronger inductive withdrawal here and the weaker, therefore, resonance donation, which is simply due to the higher electronegativity of oxygen relative to that of nitrogen. Obviously, nitrogen, therefore, is a beta electron donor, so it can donate electrons better. Now, not only esters are of a higher electrophilicity at carbon of the carbonyl group than amides, they also contain a beta leaving group. The leaving group in the case of esters, if it undergoes nucleophilic acyl substitution reactions, would be OR minus, or the alkoxide ion. So that's OR minus. Now, if amides undergo nucleophilic acyl substitution reactions, they would give an amide ion. So we need to look now at the base strength. Now, alkoxides come from alcohol, so we can look at this. We can look at the strength of the acid. Alkoxides come from alcohols or conjugate bases of alcohols, and alcohols have pKa of about 16. NR2 minus come from amines in general. Amines are very weak acids. The pKa of amines is about 40 in general, something like that. It's 36 for ammonia. In general, we can say it's about 40. So clearly, alcohols are stronger acids than amines, so that they should produce weaker conjugate bases. So this is a weaker conjugate base than amide. So this is the amide ion. So this is a stronger base or conjugate base. Now, if the alkoxide is a weaker conjugate base or a weaker base, therefore it is a more stable ion. This is therefore a less stable ion. And now, if the alkoxide, as a result of these two consequences, if it's a weak base and a more stable ion, therefore it is a beta leaving group. So the alkoxide ion, therefore, is a beta leaving group than amides, of course, than the amide ion. So in terms of leaving group ability, therefore, esters contain a beta leaving group than amides. Esters contain an alkoxide ion, which is a weaker base. We can look at again, as we did before, we can look at the acidity of the corresponding acid. Obviously, here also oxygen is more electronegative than nitrogen. So oxygen, because of that, can tolerate the negative charge more because of its high electronegativity. We can also add this to this information that we have gathered. The conclusion here is that the alkoxide ion is a beta leaving group than the amide ion. So therefore, esters are more reactive than amides in nucleophilic acyl substitution reactions. So they are more reactive in nucleophilic acyl substitution reactions than amides, not only because this carbon is more electrophilic, so this carbon is more electrophilic, but also this unit is a beta leaving group compared with the NR2 minus or the amide ion. So again, esters are more reactive than amides in nucleophilic acyl substitution reactions due to the higher electrophilicity of carbon of the carbonyl group and also the beta leaving group ability contained.